Okay, so can you see?
Yes. Thank you.
Okay, so thanks Omer, thanks Leah and Alex for organizing this, and Luigi also, I guess. So this will be a series of lectures about, so the title is Mean Field Methods in High-Dimensional Statistics and Non-Convex Optimization. And okay, I want to describe some progress that was made over the last several years about algorithms and methods in statistics, with ideas that come mostly from probability theory or physics. And this is a plan of the lecture. I want to start with some motivation, so kind of describe why people, even not probabilists, might be interested in this kind of questions and the connection with statistics. Then describe a way to get exact asymptotics for this problem via Gaussian comparison inequalities. Then pass to algorithms, and in particular first order methods, and a special first order method that is called approximate message passing, and how to get optimal first order method for regression problems using this technology. So these first things will take, first 4 points will probably take about 3 lectures, and then the last 2 lectures instead will be devoted to spin glasses and how the same type of algorithms can be used to optimize spin glass Hamiltonians. So I will first go over some background, then especially P algorithm for optimization in spin glasses, and connection to concepts in spin glass theory, in particular Parisi formula, and how to get ground state of Sherrington-Kirkpatrick and related model using these techniques. Okay, so so let me start. And okay, as a premise, I decided that since I'll try to write, I'll use this tablet for writing. Writing references will heat up part of my time, so I decided not to cite any references, any authors, except for theorems that have a name. And I'll post, actually I sent already a sheet with the references, and you can use that to look who proved what. I think that's more efficient. Okay, so my motivation, or part of my motivation, comes from statistics. So in statistics you have what do you have? You have a set of probability distribution P theta that is indexed by a vector theta that is in some set capital theta. Capital theta is a set in RD. So these are what are our probability distribution on, say, some set, some measurable space chi, and then or X, and then what you have data that are samples Z1, Zn that are IID from one of these distribution on this class, and let me write underline Z for the collection of all the samples. And what you want to do? Well, ideally you want to come up with an estimator. So an estimator is something that gives me an estimate of the parameter theta that was used to generate the data. So this is a map from Xn to reals to the D that takes underline Z and spit out theta hat of underline Z. So this is what is an estimator. And how do I measure the quality of an estimator? What is my goal? Well, I measure it typically by computing a risk function. So this depends on theta hat, in the sense it depends on the function theta hat and on the true value of the parameter. Let me call it theta 0, to estimate, to emphasize that this is true value. And this is defined as the expectation of some distance between theta hat of Z and theta 0. Okay, and this expectation is taken when theta 0 is the true value of the parameters. Okay, so this is the general setting of statistical estimation. You have samples and you want to estimate, a parameter or a function of the distributions that these samples have been generated from. Now there exists one, let's say, canonical approach to this, and the most popular approach is the following. You come up with a function, let's call it L. This is sometimes called a loss function. This is from the sample space times RD or times theta to, let's say, the non-negative reals. Okay, and you want this function to construct it such that if you define, the following object L of theta, this is, so this is sometimes called the loss function. You define the expected loss E under theta 0 of L of Z and theta. So if you define then this quantity, then what you want to happen is that theta 0 is the argmin of L of theta 0 with respect to theta. Okay, so you want the function, to construct a function script L that is an expectation, and such that if you minimize the script function, this returns the desired parameter. Well, if you have constructed such a function, then you can try to do estimation by what is called in statistics is called M estimation. In machine learning is called empirical risk minimization. But you basically, in the definition of L, you replace the population mean by the empirical mean. And then this is Zi. Okay, so the expectation of this quantity, so this is, you can write it also, the expectation over the empirical sample of L of Z theta. Okay, so if you have such a function, now if you construct this empirical mean, now what you'll do is that you define your estimator theta hat as argmin of ln of theta. And this perhaps is constrained to theta in some set. Okay, so this is the summary of what statistics is about, or a big chunk of statistics and machine learning is about. It's just a 5-minute summary, so obviously I left out some ingredient, but let me give you one standard example of this loss function L. If your probability as a density, you can take minus log of the density, and the rationale for this is that then if you compute L of theta 0, the population risk, this is minus the expectation over theta 0 of log p theta of Z, and this you must realize that is the same as the KL divergence between p theta and p theta 0. I think it's like this, plus a constant. So this is uniquely minimized as the desired parameters. So why this whole approach should work? Well, the idea is that if you have this space theta, and your population risk looks like this. This is theta 0, and instead your empirical risk ln is something that in expectation should be very close to this. I mean, expectation is equal to that. So this is ln, and expectation is equal to L, and therefore you might hope that for large, so you minimize it, so perhaps you get this point, for large n will be very close to it uniformly, and therefore theta hat will be close to theta 0. Okay, so this was my summary of what statistics is about.
Andrea,
yeah.
What is omega n? Maybe why does it depend upon n? Here we have a question.
Okay, so good question. So here I'm hiding a bunch of important things. So if you look at this figure, so this is a whole area of statistics that I don't want to enter in, but if you look at this figure here, as I said, the justification for minimizing the empirical risk is that you hope that the empirical risk is everywhere close to the population risk, right? So you hope that these two are everywhere close. Okay, but you might imagine that this is a little bit of a trade-off between two things, right? On one hand, you have n, for n large, they will be, close everywhere. But on the other hand, if your set of parameter capital theta, on which this lowercase theta lives, is very large, this will hurt you, okay? The larger is capital theta, the less, likely is that they are everywhere close, right? So you want the two to be close uniformly over the set capital theta, right? So because of that, sometimes instead of minimizing over capital theta, you minimize over smaller set, and you can make this set larger and larger as the sample size gets larger and larger. This is not always necessary, and of course will not be a main topic of this lecture, but just for be careful, I wrote a constraint there. Okay, yeah, please interrupt me if there is any question. Okay, so this is the picture. Now the classical these recipes mainly come from classical statistical problems in which let's see. So this is classically. You think of the dimension in which theta lives as fixed, and the sample size going to infinity. Okay. So this is what started, at the beginning of last century. Over the last, 10 to 20 years, people, looked and, were very interested in high-dimensional statistics. This is a set of problems in which instead, okay, both n and d go to infinity, but often, in fact, n is much smaller than the dimension. So this is kind of surprising that you can, infer or estimate a parameter vector with d entries with a sample size that is smaller than d. Here the trick or the catch is that you kind of work in problems in which theta has an effective dimension. Let me call it dimension of theta that is much smaller than the sample size. So even if the parameter vector is very long, its effective dimension in a sense is much smaller. And the canonical, or the most important example of this, is the cases in which theta, the parameter space, is the space of S0 sparse vectors. In RD. That is the set of vectors that have only S0, non-zero component, and you take S0 much smaller than D, and S0 much smaller than that. So this is the whole area of compressed sensing and sparse regression, high dimensional regression, etc. So what I'd be concerned here in the next couple of lectures will be a case in which, let's call it noisy high dimensional statistics, in which d over n is of order 1, and also the dimension of theta, if theta is simple, over n is of order 1. Okay, all of these quantities are all divergent, they are all of order 1. This is to say asymptotic. Okay. So let me give you a couple of examples. Of problems that one might look at. So let me start, for instance, one example number 1. I will not treat this example, but is an example that can be treated in this vein. You have your distribution Zi, the sample Zi are IID with the mixture distribution. So these are samples that are IID samples, and with probability half they are generated from a Gaussian with mean theta 0 and covariance identity, and with probability 1/2 are generated with mean minus theta 0 and covariance identity. In one dimension, this will look like this. So you have n samples of these types, and you want to reconstruct theta 0. Okay, so Leo is going to give a seminar, I think, and is kind of problems that he looks at in that seminar are kind of a generalization of this problem. Example number 2. Sparse regression. So the example that I gave before is mixture of Gaussians, a sparse regression. So this is a case in which my Zi are yi xi, where let's say xi is normal 0 identity, and say yi is theta 0 times xi plus noise. Let me call the noise epsilon I normal 0 sigma square. Okay, and a popular and sparse regression, because perhaps I can assume that theta 0 is sparse. That is as a constant fraction of a certain fraction of non-zero. A popular method to estimate theta 0 in this case is to minimize the following cost function. Okay, here y is the vector whose ith entry is yi, and x is the matrix whose ith row is the vector xi. Okay, so what is the rationale for this cost function is that, okay, if you want, this is minus log p theta of z. So this is the maximum likelihood component, and this is a regularization terms that promotes theta sparse. Okay. Oh wow, I'm out of time. Okay, so these are two examples. You can make up many other examples by changing, for instance, the details here. For instance, you can change the distribution of the noise epsilon, and then look at what's called sometimes robust regression, in which instead of minimizing the sum of squares, I'm minimizing another penalty. Okay, where rho is a function. Okay, perhaps you, for instance, you can take rho to be the absolute value. Okay, so these are 3 examples, and again, we are interested in studying, asymptotic behavior of these methods in these problems, and I will describe in this lecture 2 methods, in the next 2 lectures, 2 methods. One is Gaussian comparison. Okay, so these are kind of classical techniques, but they've been revived in this context fairly recently. And the nice thing is that they are really simple to apply, and they are pretty elegant. And another set of techniques that I'll talk about is related to this approximate message passing algorithm. And the advantage of this kind of method is that they are algorithmic, in the sense that they don't only give you an analysis of the problem, but also give you really an algorithm that solves it efficiently. Okay, so perhaps I'll take a little break as recommended by Luigi, and I'll check whether there is questions.
Thank you. There are a couple of questions in the chat.
Okay, one question. You want me to read them to you, Andrea?
Yeah, I don't know if I can read the questions. I don't know.
Yeah, so, okay, one question which was asked, okay, someone answered, but it's, why is this example called robust?
Yeah, okay. So this example that I mentioned here, why it in general is really called M estimation in statistics. But a special case of it, this was popular in robust statistics, and the idea, okay, the basic idea is the following. In what I described before in the square loss, you see, in the square loss, the point is that the square loss is very sensitive when you have a data point that is an outlier. Okay, so the simplest example of this thing is, of course, the one-dimensional example, right, in which you are given data points, let's say Z1, Zn that are IID with some, theta. They are equal to theta plus epsilon I, where epsilon I is some noise, right? And you want to compute the mean, some zero mean noise, and you want to compute the mean theta, okay? And so what people do since the Gauss is you compute 1 over n sum over r, or before Gauss probably, Zi, okay? Which implicitly is minimizing sum over I of Zi minus theta square, okay? So where this comes from is from minimizing this cost function. But something that you know very well is that the mean is very sensitive to an outlier. If you have a single outlier, this will hurt you a lot. And so something that is sometimes better to do is compute the median, for instance. And so this corresponds to changing the cost function, right? Instead of minimizing the sum of square, I minimize the sum of absolute values. So by changing rho, I can obtain more robust estimators. So this gives the median. I hope this answers the question.
So here's one. We are not going to cover the Bayesian interpretation of the penalties, or that's the question.
No, I'm not going to cover any Bayesian interpretation. Of course, you can think of, if you look, for instance, a cost function like the lasso, you can give a Bayesian interpretation in the sense that this is the mode of the posterior when the noise is Gaussian and when the prior is Laplace. But I don't think, for instance, the Bayesian interpretation is very illuminating in this case. And actually, I think it's misleading in this case, in this specific case. And but we'll discuss something that is Bayesian in nature in the lower bound. What follows probably tomorrow.
Okay, I'm not sure exactly what this question is referring to, but it says, or absolute values equal to rho, perhaps? I'm not sure.
I think that was referring to the robust regression answers.
Oh, okay.
Yeah, so here in this case, I'm thinking of the sum over I rho of Zi minus theta.
Yeah.
Okay.
So in this case, I'm taking rho to be the absolute value function.
Yeah, I think
All
that's
right. So today I'll try to describe this approach based on Gaussian comparison, and the basic theorem is the following inequality. Okay, so this is known as Gordon inequality, and it says the following: you have two Gaussian processes, finite Gaussian processes. So these are indexed by some finite set, and so they are centered, and T and S are finite. And you assume the following. That, okay, the variances are equal. Point one. Point two, you assume that if you keep this first thing, the first index unchanged, oh, this is minus x, sorry. So this goes in this direction. For all T1 different from T2. Different or equal, doesn't matter. And the third condition and this is for all S1. And all T1, T2. Then if you assume these three conditions holds, then I'm gonna look at the mean over S, the max over T of XST, and then gonna allow me some shift Xi, and the claim that this is, dominates stochastically the mean over S, the max over T of YST. Okay, and by dominates, so this is for any set of Xi. xi a real number. And dominate stochastically. What I mean by this is that okay, let's say that A Okay, so this is Gordon inequality. I will not prove it. It's not a difficult proof. It's something quite simple. You probably, it's not that often taught. Something that is more commonly taught is it's not often so often taught, perhaps because max-min problems perhaps are not so popular, but something that is more popularly taught is Fernick inequality, and you can see that this generalizes Fernick inequality that you recover if you, for instance, set one of the inner optimization problem to be trivial. So if you take the set T to be of size 1, so the maximization problem becomes trivial, and therefore this is inequality between minima or maxima that is the same, and you have the usual thing that if one of the two Gaussian distances dominates the other, then the minimum dominates stochastically the other. Okay, so this is the inequality. Perhaps I should show it again. So the three conditions to check are these ones. And okay, so what I want to describe is how it's applied to one of these statistical problems. Okay, it's not complicated. It's just a matter of choosing things in the right way. And the convenient corollary is the following. Take two sets U. Okay, I'll take U to be in RD, say, and V in Rn. Okay, and just to be careful, let's say that they are compact. And let's take a function Q that is continuous. Probably, okay, and then I'll define two quantities. Okay, first of all, let me take a matrix G that has element Gij that are IID normal 0, 1, and two vectors G normal 0, 1, IID, and H. Okay, so I'm given two, a matrix. The matrix will be n by d and two vectors G and H. Okay, and then I'll define two quantities, two max-min problem. L star, this depends on the matrix G, and this is the mean over U in capital U of the max over V in capital V of V G U. This is scalar product plus Q U V. Okay, and the other one will be C star, or okay, let me call it B star. Of G and H. This will be the mean of the max of, and now I'll do something much simpler. Okay. Okay, so I have these two problems. Then the claim is that okay, let me write it here. The probability that L star. Okay, let me omit the argument. For any U. Okay, so in other words, B is a stochastic lower bound to L. So this gives you one side. Further, if the problem min max is concave, convex concave, so what I mean by this, I mean that this optimization problem is, so you see each of these optimization problems, there is a part that is linear in U and linear in V, the first part. Okay, at least the first, if you look at the first optimization problem, there is a part that is linear in U and linear in V. And then there is another part that is a function Q, U, V. So you want this overall objective to be concave in V and convex in U, and the two set U and V to be convex. Okay, so if that happens, then you have the reverse inequality. So the nice thing is that this basically, in the case of convex concave problem, if B star concentrates, this gives you upper and lower bound, and the upper and lower bound will basically concentrate around the same value. So the typical picture here is that the probability that B star is bigger or equal than U, as a sharp threshold around a typical value, and therefore if you use these two inequalities, so this is, let's say, the typical B, this is, let's say, U. And this is the typical B. So it has a sharp threshold around a certain B, in which it goes from 0 to 1, this probability. And therefore, if you use these two, this bound and the previous bound and this other bound, then you get the probability also that L star must also concentrate around this lowercase b. Okay, now what is the interest of this is that if you look at these two optimization problems, the first optimization problem is this part that is, okay, is this QUV that is general, but depends on U and V also the first, even if QUV is simple, this bilinear part in V and U depends in a tricky way on U and V. Instead, the second thing, the second optimization problem is much simpler because is basically if you treat norm of V and norm of U as constants, it becomes separable in U and V. So it amounts to, optimizing each coordinate of U and each coordinate of V separately. So if you forget, or another way to think about it is that if you forget the norm of V and the norm of U here, this problem is basically linear, modulo the function QUV. So the second problem is much simpler to analyze than the second. So I claim that this corollary is really, as I said, a kind of immediate consequence of Gordos theorem. Once you come up with this comparison, it's just a matter, these are two Gaussian processes. You're optimizing two Gaussian processes that are indexed by vectors V and U. Okay, so there is a trivial technical difficulty is that, okay, V and U range over sets that are not countable, not finite and not countable. But okay, I chose my assumptions here in such a way to make this easy, right? I can discretize the sets capital U and capital V because they are compact, and since Q is continuous, I'm in good shape. Okay, so going from finite set to infinite set is not a big deal here. The only thing that we have to check to apply Gordon is to check that the covariances are in the right order. The covariances of the two processes are in the, this Q plays the role of the constant Xi. The only thing that I have to check is that the covariances are in the right order. And okay, I'll do this quickly, this exercise. Okay, so I have these two processes again, what I call X in the Gordos theorem. This is B times G U plus U times H V. And what I call the Y is V times GU plus, and okay, here is a trick. I'll add, Z times norm of U times norm of V, where Z is another scalar random variable. This Z might make my life easy. Notice that this Z doesn't appear in my optimization problem here because I wanted to keep things clean, and I'm paying for the sloppiness of not putting the Z here by this factor 2. So this factor 2 is basically the effect of conditioning of Z being positive or negative. But you understand that this Z is not play a big role, it's just a single scalar. So now I'll check that these two processes are in the right order as required by Gordos theorem, and okay, so the calculation that you have to do is computing XU1 V1, YU2 V2 minus expectation of XU1 V1 XU2 V2. And okay, you see, when you compute the covariance of U, you get a piece that comes from this guy and a piece that comes from this guy. Okay, and so there's those two pieces are one is the piece that comes from the matrix term as the form of U1 V1 times that doesn't make sense. U1, U2 times V1, V2. And the piece that comes from the Z guy is, trivial, it's simple, U1, U2, V1, V2. And then there is you subtract the dx, contribution. And again, there is a piece that comes from this term and a piece that comes from this term. And of course, they are symmetric, so they are simple to compute. And you get is one is U1. The first one is U1, U2 times V1, V2. And the second one is V1, V2 from H times V times U1. Oh, jumped around. U2. Okay, so if you put everything together, this difference is now magically, let's see what I should write, is magically U1, U2 minus V1 minus U1, U2 times V1, V2 minus V1, V2. Okay, and because of Cauchy-Schwarz, these two are positive, so this is always positive, and then you check that this implies all the conditions that you wanted. Okay, so this proves this corollary, the first part. Okay, how do you prove the convex thing? This is just a duality argument. if the problem is concave convex, then this L star is a mean over U max over V of VGU plus blah, blah, blah. And this is equal to max over V mean over U. And here I'm using the concave convexity. Okay, and this is, okay, this is of course minus of the mean over V, the max over U of V minus G U plus blah, blah, blah. And now this minus G matrix is really, distributed as the G matrix, okay? And therefore I can get, a bound on the other side by this argument, by the same argument as before. Okay, so this describes a general corollary. Now I want to describe how to apply it. And instead of taking the most general setting, I'll take the lasso. So how to apply it? Okay, the basic idea is, okay, I want to study, if you remember. So in the lasso, I wanted to do a sparse regression, and my cost function looked like 1 over 2n, and then there is y minus x theta square plus lambda theta 1. Okay. Okay, and what I'm interested in is I'm interested in the minimum over theta of ln of theta. Okay, so this is not a min max problem, but I can write it as a min max problem simply as the mean over okay, first of all, let me do something. This has a first difficulty is that here y and x are correlated, so it doesn't take the simple form as we were describing before, but I can use the fact that y is equal to x times theta 0 plus a Gaussian vector, and I can define theta minus theta 0 equal u. And so I get that this is the mean over U in RD of 1 over 2n. And then sigma W is a Gaussian vector with IID, Gaussian coordinates, minus x U. Okay, now this is very nice because now all the randomness, all the Gaussian randomness is in this matrix X that is exactly, up to R scaling is just the same as our matrix G in the little lemma. Okay, and now I want to write this as a minimax problem. And this is just, simple. You write this as, oh, sorry, forgot the max over V. And then there is 1 over n. Then and then minus sigma W times V plus lambda times, okay. Okay, So this takes now exactly the form that I described before. This piece is VGU, and all the rest is the function Q. Okay, and at this point I can characterize. So by using Gordos theorem, I can prove that the minimum concentrate around a certain value. Now, this is not what I'm really interested in. What I'm really interested in is computing questions, properties of theta hat, of the minimizer. And the way I go about it is simply saying, okay, I define the minimum of this over a set S. And I use Gordos theorem to compute the limit of this value. And if the limit of L star of S is bigger, okay, I just use the fact that if strictly where this is the global minimum, this implies that theta hat is in S complement. Well, so by choosing in the right way the set S, I can show that theta hat is in a certain other set. So for instance, I can take typical thing that I want to prove is that theta hat minus theta 0, 2 norm square, concentrate around some value, so converges, for instance, in probability to some limit A. So I'll take S, the set of theta, such that theta minus theta 0 square minus A is bigger than epsilon. All right, so by proving that the minimizer in this set is bigger, I can prove that this convergence, this kind of convergence theorem. Okay, so this is the basic idea of how this is done. Now let me describe in 5 minutes. I want to try to describe the result, the typical result that you get here for the lasso, and I'll describe one precise theorem. I'll just state it, so the setting is you take n and d goes to infinity, and then n over d goes to some ratio delta, say, and I'll assume what I'm assuming about theta 0 is that if I look at the empirical distribution of theta 0, this converges, say, in W2 distance to some limit low, p theta. So now the limit is described by a set of, solution of a set of equation. So I call theta star beta star the solution of, and the solution is unique, of these two equations. Theta square equals sigma square plus 1 over delta expectation of eta theta plus tau z minus theta square. Okay, and this is the first equation, and the second equation is beta equals tau times 1 minus 1 over delta probability. Okay, let me write it this way: theta plus tau z absolute value Okay, so these are here, these equations are with respect to capital theta that has the distribution p theta, and z that has normal 0, 1, and the two have to be independent. Okay, so okay, I will not describe at the moment where these two equations come from, but you solve these two equations. This come basically one way to derive it is to analyze this Gordon problem. Here, okay, there is one thing I didn't define. Okay, I was a bit quick here. So here there is another parameter here that I call tau lambda over beta. Here I didn't define this function eta of x and u is in a special function is x minus u positive part times sine of x. Okay, so it's a function that looks like this. It's 0 between minus u and u, and then it's linear outside the interval minus u. Okay, so but I solved these two equations in tau and beta. Okay, and then this will give me the limit value of the limit distribution of the lasso in the following sense. Okay, 1 minute. Let me just state this thing. I look at mu hat lambda. This is 1 over d sum over I 1 to d delta theta 0 I theta at I. So this is the joint empirical distribution of the true vector and the lasso estimate. And then on the other hand, I let me call mu d lambda is the law of theta and theta eta et tau lambda over beta star of theta plus tau z. Okay, and the theorem is that the probability that the distance between mu hat and mu hat d is bigger than epsilon is smaller than some constant of epsilon e to the minus n, some other constant of epsilon. Okay, so basically this is, what is telling this theorem is give you the complete joint empirical distribution of the true parameter vector and of the lasso estimates, and in terms of the solution of these two equations. So you solve these two equations. This is very easy. This gives you two parameters, tau and beta, and then you compute these two random variables. One is theta, of course, and the other is eta applied to theta plus Gaussian noise. You compute these two, and I'm sorry, here I messed up my formula. Okay, and then these two are close in the sense that their distribution are close, for instance, in Wasserstein distance. Okay, so I'm sorry I went over time, but I guess that's all for today.
That's okay, thank you. So we will now stop the recordings. We will unmute all the participants to thank Andrea.